Thank you for your interest in the Water Commons Index. My name is Matt Grice, and I'm an architect in Santa Barbara, California. I've been working with others in the design and environmental data science community to improve water management practices related to land use development. In this video, we'll be sharing some preliminary approaches and tools we've been working on. We hope to engage a wider community of practitioners for their improvement. Currently, a few-sizes-fits-all approach is generally applied to mitigate runoff and stormwater pollution. We believe a more strategic and holistic approach can be taken.
By identifying and incentivizing the best parcels for water recharge, we can maximize the benefit to our water commons. Now, this not only includes our aquifers, streams, and reservoirs, but also our native landscapes and the biomass that goes with it. Each site has a unique hydrological context, and each development has a unique set of land use requirements to accompany it. Reducing runoff is always an incredibly project-specific problem. The Water Commons Index provides a simple interactive tool to choose the most ideal permeable practices geared towards individual sites based on each site's specific opportunities and constraints. Imagine we have a site that's covered completely with permeable surfaces. Combined, let's assume these surfaces are capable of absorbing 2 inches of rain per hour. That means during a storm with an intensity up to 2 inches per hour, the site would create zero runoff, and this means it would satisfy 100% of its recharge potential. We could say the site is balanced with respect to its recharge potential. But what happens when a development is proposed and a large portion of the site becomes impervious to rain? If the balanced portion of the site is already at capacity, then all of the rain hitting the impervious areas will shed off the site, turning into runoff. If we want to avoid this, then we must improve the performance of the remaining permeable areas so that they counterbalance all the new runoff created. Land use codes and government approval to proceed with any development depends on this concept. If too little permeable area is remaining, then it may be difficult to compensate for a site's native recharge potential. Now let's examine what we mean by recharge potential. The recharge potential of a site is directly related to the permeability and overall capacity of its topsoil. The process of recharge, therefore, always begins with soil recharge. Once this is complete, zones directly connected to the soil can then be recharged as well. Extending up from the soil, a site's biomass is first in line to get recharged. Nearby streams and creeks are next to be replenished as water percolates laterally through the soil. Last but not least, aquifers located below a site will be recharged, assuming, of course, the water has had a chance to infiltrate far enough down past the subsoil. Ultimately, it is our goal to find a pathway to rebalancing the site using the permeable surfaces available. This usually means introducing new permeable practices able to boost the recharge capacity within more limited areas throughout the site. The second graph represents our Permeable Practices Index. It is used to track the actual performance of specific permeable practices developed on a site. Options for best practices are primarily based on the infiltration capacity desired, but topographic and regulatory restrictions will likely eliminate some of these options. Once the best options are determined, the tool allows us to analyze cost and environmental issues before making any final decisions. With this tool, the best practices will be the ones that not only prevent runoff and stormwater pollution, but will do so while also fulfilling a site's unique recharge potential. This is a step we must take in order to both secure and protect our water supply and also preserve and sustain our watersheds.